going to explain to you how simultaneous equation models are to be estimated, and a little bit of theory about what are simultaneous equation models, when are they used, under what circumstances they are used. So I'm going to make a brief presentation of that. So simultaneous equation model stems from this concept of endogeneity. Now, an endogenous variable is a dependent variable, and an exogenous variable is an independent variable. The difference is the endogenous variable will always be measured with a certain amount of error. So in other words, an endogenous variable is stochastic. Whereas an exogenous variable, which is an independent variable, is strictly supposed to be deterministic. The problem arises when the exogenous variable is correlated with the error of the model. When the exogenous variable is correlated with the error of the model, you get a problem called simultaneity bias. So where the exogenous variable is considered as an exogenous variable, but does not strictly behave like an exogenous variable, you get this problem of endogeneity. We have assumed that the error term in a linear regression model is uncorrelated with the explanatory variance. So that is the assumption. It's one of the assumptions of fitting a single equation. That the error term of the model should not be correlated with the independent variable. Okay, only then they are considered to be strictly independent and an explanatory. Sometimes it is very unrealistic to treat the explanatory variable in a model as given or exogenous. It's quite likely that in subscript you should know when that happened. There is no test for it. It is something that you know more out of theory and out of practice. In such cases, it can be argued that some of the explanatory variables some of the explanatory variables are correlated with the error term in the equation, and then the regression becomes biased, and that is where we use the simultaneous equations. Okay, so that's basically the concept of endogeneity. So there are many reasons why the error term are simultaneously correlated with the explanatory variable, but the OLS estimator will be biased and inconsistent. This is what you should remember, because what we want is estimates which are unbiased, and they should be consistent. In such cases, we need to look at alternative estimators. Okay, so here we use simultaneous equation models, which are estimated using different methods, such as two-stage least squares, generalized method of moments, and so on and so forth. So this is basically what you do. Now, let us think of a regression. Okay, you are trying to find out what are the factors that influence the GDP of a region or a state or a country. So the explanatory variables will be agricultural production, industrial production, trade, maybe exchange rate, foreign direct investment. So this strictly looks like a single equation model, and you'll be under the impression that you can estimate a single equation model where GDP will be the dependent variable and all the other variables that I mentioned will be independent variables, and there should be no problem. But we know that agricultural production, industrial production, and trade are not necessarily exogenous. They are dependent on other variables. Like industrial production will depend on foreign direct investment, it will depend on how much we export maybe. So they will be. Similarly, agriculture will depend on the technology, depends on what is the rainfall, and very many other things. So in such cases, using a single equation model could lead to wrong results. And that is when we bring in what the concept called a simultaneous equation is. Now, in a simultaneous equation model, you model the system. Rather than looking at one part of the system, which is GDP, you try to model the whole system of the economy. So the model constitutes a system of so the model will consist of a system of equations, which capture the relationships involved in needing involved. You need it before you can really determine the value of the variable that you're interested in. Okay, so this implies that at least one of the relationships includes more than one endogenous variable. You'll understand this as we go along. So therefore, a simultaneous equation model is a statistical technique used to analyze a system of interdependent relationships among multiple variables. Unlike single equation regression models, that assumes a one-way causal relationship, simultaneous equation model recognize that in many real-world scenarios, variables can simultaneously influence each other. And this means that variables can be both a cause as well as an effect within the system. Okay, so this is basically what's it. So in a simultaneous equation model, you're looking at in the general equilibrium frame, not in the partial equilibrium frame. Okay, and what is the core idea? The core idea is the simultaneous equation models are used when simultaneous or reciprocal causation between two or more endogenous variables exist. An endogenous variable, as I already explained, is one whose value is determined within the model. That's endogenous. So the endogenous variable is decided within the system. The model can consist of multiple relationships, whether each equation represents a relationship between the dependent variable and one or more explanatory variables. Exogenous variables are those values which are determined outside the model. So this basic distinction you have to remember. And the simultaneous equation model, the original simultaneous equation model, are called the structural parameters of these equations, which reveals the direct effects of one variable on another within the system. You should remember this. So the structural parameters reveal the direct effect of the variable on one another. You'll understand this as we do it. So why do we use simultaneous equation models? So we use simultaneous models when you have this problem of an indigeneity, which I mentioned earlier. Ordinary least square estimation of a single equation in a system of simultaneous equation model can lead to biased and inconsistent parameter estimates. I'll show you this with an example. This happens because if an explanatory variable is also determined within the system, it is likely to be correlated with the error term in the equation. Structural equation models provide methods to deal with this interface. Let me give you this example. Now, when you in a regression where GDP, per capita GDP is a dependent variable and index of industrial production is the independent variable, then you know the index of industrial production also depends on the employment, it depends on the credit flow, it depends on the interest rate, it probably depends on the foreign direct investment. So the independent variable in the first equation is not strictly exogenous and it becomes endogenous. In such cases, the error term could be correlated with the independent. That's the basis. So that's one reason to handle this endogeneity bias. Another reason why you use simultaneous equation models is to capture interdependencies. And we know in economics and in real life situations, there's a lot of interdependency between economic variables. Such equation models allow the analysis of complex systems where variables influence each other directly and indirectly through a feedback loop. It's used very extensively in policy analysis and in forecasting because it has this ability of capturing all interrelationship and interdependencies between variables. Okay? So what are the components of a simultaneous equation? The components are, one is the endogenous variable. As you can see, first and foremost thing is the endogenous variable. Variables determined within the model, within the system. Then you have the exogenous variable, which comes over here. Okay, just separate it out. Then you have the concept of exogenous. Okay, so exogenous variables, which are strictly exogenous in the sense they are decided outside the system, and they are considered to be exogenous variables. Then you have the structural equations. So you should know these concepts. You have the structural equations, which really capture the real relationship that you're looking at. The relationship that the real life relationship that occurs to you will be captured through the structural equations, and they represent a theoretical relationship between the endogenous and the exogenous variables, reflecting the underlying economic, social, and other processes. The aim is to capture the direct causal effects. What is causal effects? Then, related to this, you have something called as the reduced form equations. So these express such endogenous variables solely as a function of the exogenous variables and the error term. They are derived from the structural equations and are useful for estimation and prediction. So this is basically what are the components of a simultaneous equation model before we get straight into the topic. Then the very important thing that you should remember in simultaneous equation models is you should know which estimator you're going to use. To estimate a system of simultaneous equations, you have to know the appropriate estimators. There are many estimators. Like you don't use OLS. You use two-stage, you use indirect least squares, you use two-stage least squares, you use three-stage least squares, and you use full information maximum likelihood. We'll be discussing that. So in order to decide which estimator to use, then there's a very important step called the identification. Okay, it's called identification. You should identify whether the equation is over-identified, under-identified, or just identified. So an equation in a system is identified. An equation in a system is identified if it is possible to obtain unique estimates of the structural parameters from the reduced form parameters. So you can estimate the parameters of a simultaneous equation system, that means the equations are identified. So there are certain rules which we shall discuss that. There is something called as an order condition and a rank condition. To check whether the equation is identified, exactly identified, over-identified or under-identified, is what we do in this process of identification. Then, depending on whether the model is identified, then you use these different methods, and these are the different estimators. You should know that indirect least squares applicable to equations which are exactly identical. It involves estimating the reduced form and then deriving the structural parameters from the reduced form. You'll understand it when you do it. The second is called the two-stage least squares, a common method for over-identified equations. It involves using instrumental variables, typically the exogenous variables, excluded, that you'll understand later. So you will use for the time being, you should just remember that two-stage least squares is used when the system of equations when the equation is over-identified. Okay, over-identified to create the. The third is called the three-stage least squares, a full information method that estimates all the structural equations simultaneously. So this is the joint estimation, where the two-stage least square is a single equation model. So full information method is the estimation of all the structural equations simultaneously, taking into account the correlations between the error terms of the different equations. It is more efficient than two-stage least squares if the error terms are indeed correlated. So just remember that. And the fourth method is called the full information maximum likelihood estimate. Another full information maximum estimates are all parameters are estimated simultaneously for maximizing the maximum likelihood of the entire system. So these are the four methods that you use when you use simultaneous equation. Now coming to this concept of endogeneity and causality. Now as you can see in this equation, y1 and y2 are endogenous. x1 and x2, sorry, this one x1, this should be x1. x1 and x2 are exogenous, and which means, but when you see this, y1 is terms. Okay, this should be y2. That is, y1 depends on y2, and y2 depends on y1. y2 depends on y1, and this could be x1, and this could be x2. Yeah. Okay, so in this equation, y1 and y2 are considered to be endogenous. Okay, u1 and u2 are the error terms, which are not supposed to be correlated. But since this is an endogenous variable, it's quite likely that y2 will be correlated with u2. And y2 will be correlated with u2. And that is why we use simultaneous equations. So we know what are endogenous variables and exogenous variables. So we know that y1 and y2 are endogenous variables. And strictly x1 and x2 are the exogenous variables. Okay. Cases where the OLS estimator cannot be saved. So in the previous section, we've shown that, no, strictly speaking, what you need to remember is when the error term, that is the expected value of ET(xt) is equal to 0, then there is no problem of endogeneity. But when ET(xt) is not equal to 0, then you have a problem of endogeneity. That means, strictly speaking, X will be an endogenous variable. And then you have to use a simultaneous model to solve this. Okay, so that's it. So you just remember that. So when the model contains a variable such as, there is a specific case, let us know this. So then we have a concept called a proxy or an instrumental variable. Now, instrumental variables are a part and parcel of simultaneous equation. Okay, a proxy variable is something that you use as a variable in place of some other variable. So it must be emphasized a proxy variable is not an instrumental variable. So instrumental variable in simultaneous equation models has got a specific connotation. Whereas proxy variables is just a variable that you use instead of a variable that you want to use, which you don't have a measurement on. You do, like, for instance, you may not have a measurement on happiness. So you'll have to use a proxy variable to capture that happiness, some things which are not measurable. So thus, in instrumental variable framework, it is implied that we do not regress y on z to obtain estimates. Okay. Now, this is very important. Now, how do we check the instrument validity? Because instrument variables are just something that are generated by you. You will come to know. So keep in mind what I have talked about. Keep in mind this concept of a general instrument. They write it as IV. This is not 4, it is IV, which is instrumental variable. While it's hard to answer for general instrumental variable regression, in the case of a single endogenous regressor X, one may use the following rule of the thumb. So remember that. So how do you check whether the instrumental variable is valid or not to be included in a simultaneous equation framework? Then you have to do this test. Compute the F test, which corresponds to the hypothesis that the coefficients of Z1, Z2, M1 are all 0 in the first regression. So if the F statistics is less than 10 million, the instrumental variables are big. So in other words, if the F statistics is non-significant of the instrumental, reduced form equation, then you say the instrument is a weak instrument. Isn't it? The instruments are weak such that the two-stage least squares estimates of the coefficients of X is biased and not valid. Not valid statistical inference about the true value can be made. You should remember this. So you should remember that you should not use an instrumental variable randomly. Rather, you should use it after you have done this test that the instrumental variable is significant. If it is not, then you say that the three-stage or a two-stage least square estimates of the coefficients will be biased and not valid for statistical inference. So if an instrumental variables are weak, there are two ways to proceed. If the instruments are weak, discard the weak instrument and find a stronger instrument. While the former is only an option if the unknown coefficients remain identified when the weak instruments are discarded, the latter can be very difficult and even may require a redesign of the whole study. That you'll understand when you do it. So the rule that you should remember is, if an instrument is weak, try to discard it and replace it with a stronger instrument. But when you replace it with a stronger instrument, it amounts to recasting the whole simultaneous equation system. So stick to the weak instrument, but use methods that improve the two-stage, three-stage in the scenario. For example, the limited information maximum likelihood estimates would be a better option to consider. Okay, so we have talked about this. We have talked about this, that regression equations study relationships, but we have a problem. Okay, the instrumental variable in macroeconomics, there are a wide, this is very important. Instrumental variables have their own interpretation, and that is the in macroeconomics, there are a wide range of models that consist of a system of equations that simultaneously determine a number of endogenous variables. So consider, for example, a demand and supply equation, both depending upon price, and the equilibrium condition that states that demand and supply should be equal. So the resulting simultaneous equation determines quantities and prices, and it can typically be said that the prices determine the quantities or the quantities determine the prices. Similarly, in the Keynes model also, you use this concept of integral. Now you'll understand what is instrumental variable. Now these are my structural parameters, which are decided by theory. So I've given you a hypothetical example where I said the per capita GDP is dependent on index of industrial production, agricultural production, exchange rate, exports, imports. X is exports, Y is imports. Then I treat this as an independent variable, the dependent endogenous variable. So index of industrial production depends on GDP, doesn't matter. Depends on foreign direct investment and also depends on agricultural production. You can add to the list. I'm just showing you, it's only to demo. Then I'm also assuming that agricultural production is also an endogenous variable. So then I have to declare it. So wherever in my single equation model, I find an endogenous variable, that variable should also be explicitly stated as an equation. Now, agricultural production is a function of rainfall, maybe exchange rate, and this is also time, technology. Then exports. Now, exports is a function of GDP, index of industrial production, agricultural production, and the exchange rate. Imports is a function of GDP and the exchange rate. Correct? So we are kind of creating a set of simultaneous equation models. So given the model, no obvious instruments arise. In fact, this is a common problem in models with measurement errors due to inaccurate recording. The task is now to find an observed variable that is correlated with xt, that's indeterminable, but not correlated with ut. Now, I should get variables which are, now for instance, these two, which are dependent variables, will definitely be correlated with the error term. So I need to find out a variable which is not correlated with the error term. That is, I should find out another variable for this. I cannot use index of industrial production directly. Neither can I use agricultural production directly. So I have to find an instrumental variable. So if we can find a variable, we can apply instrumental variable estimation. Mainly, due to the problem of finding a suitable instrument, the problem of measurement error is often ignored in empirical work. Since squares is consistent, we might instead use an instrumental variable. Since least square is inconsistent, we might instead use an instrumental estimator. Meaning, if you use an OLS estimator for this, it will not be efficient. It will be inconsistent. So he said we'll use an instrument instead of that. So instead of IIP, I'll use IIP hat. And instead of AP, I will use AAP hat. Now, in this system of simultaneous equation models, you will notice I've marked certain variables in red. Now, these variables which are marked in red are considered to be the exogenous variables. Foreign direct investment decided outside the system, exogenous. Rainfall, which is decided outside the system, exogenous. Price outside the system, exogenous. Technology outside the system, exogenous. Exchange rate outside the system. So now we have to do this. When you do a simultaneous equation, we'll first set up the set of equations. To see that no endogenous variable goes unrepresented as an equation. So you will have as many equations as you have endogenous variables in the system. So it means that you have 5 endogenous variables. And looking at that red variables marked in red, I have 1, 2, 3, 4, 5. I've also got 5 exogenous variables. There is no requirement for it to be the same. It just happens to be the same. But what is more important is what follows. The only variable in the system that is not correlated with the disturbance is x. So if more than one explanatory variable is considered to be endogenous, the dimension of x to I is increased accordingly, and the model reads, that's what you've shown on the top. So to estimate the equation, we need an instrumental variable for the x2. Now for this x2, now there's an x in this model, so I can't use this. I should use an instrumental variable. That means if we have 5 endogenous variables, we need 5 different instrumental variables. So you can see this is an endogenous variable, this is an endogenous. I need 5. So strictly I know I've got 5 endogenous variables. I should have 5 instrumental variables. Then instrumental variables are very strict. So endogenous variables jointly are also called the jointly determined variables. A variable which is explained by the functioning of a system and values of which are determined by the simultaneous interaction of relations in the model are endogenous variables or jointly determined variables. What is important now is the exogenous variables, which are also referred to as predetermined variables. The variables that contribute to provide explanations for the endogenous variables and values of which are determined from outside the model are exogenous. Exogenous variables help in explaining the variations in the endogenous variable. It is customary to include past values of endogenous variables in the predetermined code. So wherever you're using a lag-dependent variable, that will be treated as an exogenous variable. Yeah. So since exogenous variables are predetermined, so they are independent of the disturbance term in the model. So they satisfy those assumptions which explanatory variables satisfy in the usual relation. Exogenous variables influence the endogenous variables. So this is a little bit of theory which you can read this thing. Okay. Now let us now move straight into an empirical example. So many of these concepts will get clarified over there. So what do you mean by identification? So when you fit a simultaneous equation model, remember the first thing that you have to do is create your sets of systems of equations. Now there is no rule. It has been done purely based on your knowledge of theory. So there is no thumb rule where you can develop the equations in a particular way. There's no iterative procedure by which you can iterate and get the system of simultaneous equation models. But the system of simultaneous equation models give you the structural parameters. So but we need to identify. In order to solve simultaneous equation models, you have to go through this process of identification. So by identification, we mean that whether the numerical estimates of the parameters of the structural equation can be obtained from the estimated reduced form functions. So if this can be done, we say that the particular equation is identified, else equation is considered under consideration is over-identified or under-identified. Okay. So once you go through this process of identification, you will come to know whether the equations are over-identified or under-identified. So there are three types of identification: over-identified. So the estimation of when an equation is over-identified, the estimation of parameters is not at all possible because there's not enough data. If it is exactly identified, the estimation of parameters is possible. The OLS of the reduced form equation leads to unique estimates of the structure. I'll explain that with the example. Usually, we would always want our equations to be over. So in order to estimate simultaneous equation models, either they should be exactly identified or they should be over-identified. So in an over-identified equation, the estimation of parameters in this case is possible. The OLS estimate is of reduced form coefficients leads to multiple estimates of the structural coefficients. Now this is the rule. This is the rule. Now capital K is the number of exogenous variables in the system. Small k is the number of exogenous variables in the equation. So the rule is capital K minus small k should be less than G minus 1, then you say it's identified. What is G? Number of exogenous variable in the equation. So in this illustration, capital refers to the system, small case refers to the equation. So if I give you a big G, then you talk about the total endogenous variables in the system. In that case, it was 5. So carefully look. So when k minus small k is less than G minus 1, it is under-identified. If k minus small k is equal to G minus 1, you say it is just identified. So in other words, if capital K minus small k is equal to G minus 1, it is exactly identified. If capital K minus small k is greater than G minus 1, is called over-identified. He's put it as D and he's used D as a criteria. So K is the number of exogenous variables in the system. Capital K is the number of exogenous variables in the system. Small k is the number of exogenous variables in the equation. G is the number of endogenous variables in the system. Small g is the number of endogenous variables in the system. And D, of course, is the differential that you can ignore. Okay, so this is the rule. So the first is apply ordinary least squares to each of the reduced form equations and estimate the reduced form coefficients. Now, how do you do indirect least squares? We talked about the indirect least squares. So indirect least squares happens when your capital, so it is rearranged. This is just capital K minus small k should be equal to G minus 1. Okay. Then in such cases, what you do is apply an ordinary least square regression on each of the reduced form equations and estimate the reduced form coefficient values. Find the algebraical relationship between the structural equations and the reduced form coefficients, and then find the structure. So what they say is when your equation is just identified, that is capital K minus small k is equal to G minus 1, then what you're supposed to do is first estimate the reduced form equations. And from the coefficients of reduced form equations, you get the coefficients of structural equations. You'll understand it a little clearer. Now take this example. Now you see. Now let us first go and see what is capital K. Capital K is the total number of independent variables, exogenous variables in the system. I marked them as in red, so for your convenience. 1, 2, 3. You don't count this, it's already here. 1, 2, 3, 4, 5, 6. You don't count this. 7. You don't count 7. So capital K is 7. Capital K is 7. So I'm going to, now when we do this identification, I do it equation by equation. So I take the first equation. So I know the total capital K is 7. How many exogenous variables are there in this equation? There is only one. So 7 minus 1 is greater than how many endogenous variables are there? 1, 2, 3, 4, 5. Okay, I made a mistake. Okay. 1, 2, 3, 4, 5. So I made a mistake. Right. Okay. Oh, sorry. It's small g, my mistake, my mistake. So capital K minus small k is 7 minus 1 should be greater than small g. This 1, 2, 3, 4. So 4 minus 1. So 7 minus 1 is 5. 5 is greater than 3. So this equation is over identified. And I will use either two-stage least squares or three-stage least squares to estimate of holding information maximum. Now come to this. Capital K is 7. The small k is 3. 7 minus 3. 7 minus 3 is 4. The number of, oh, here again, the mistake. 1, 2. Okay, the dependent variables are endogenous variables. Don't count this. Two dependent. So 2 minus 1. So 7 minus 3 gives you 4. 4 is greater than 2 minus 1. This is also over identified. You by default, you can buy the 7 minus 4, 2, 3, 4 is greater than, there are no dependent, 0 minus 1. So it is greater. So this is over identified. This is also over identified. So they now you know what estimator to use. So for the first equation, I will use two-stage least squares, three-stage least squares, depending on my convenience. I will use two-stage least squares. I will use two-stage least squares. I'll use two-stage least squares. I'll use two-stage least squares because all of them are over identified. Okay. Now I revised the parameters. You know, you have to go on revise. I said it's not today's capital investment. This is for an investment, capital investment. So I say capital investment of the last year. So this type of manipulations you can use. So the moment you use K of course is the capital investment. So that becomes an endogenous variable, capital. Okay. So if I take, look, take agricultural production. Now, agricultural production is a dependent variable. So the current agricultural production depends on the lagged agricultural production. The lagged agricultural production becomes an exogenous variable. Okay, because it's predetermined. So here I've also found out, I've done a process of identification. You can pause it and you can study it for your own and you'll understand. Now, what is important is I should identify all the exogenous variables. 1, 2, 3, whatever. There should be no overlapping. So 1, 2, 3, 4, 5, 6, 7. Okay. This is how you get the reduced form equation. So you should remember this. So you get the reduced form equations by regressing each endogenous variables. There are 1, 2, 3, 4, 5 by all the exogenous variables in the system. 1, 2, 3, 4, 5, 6, 7, 8. I've taken this 8. Okay. So you'll notice that the exogenous variables are the same. So you get the reduced form equations by regressing each endogenous variable by all the exogenous variables in the system and not in the equation. So I've got a regression for GDP, I've got the regression for IIP, I've got a regression, and this is how I get the reduced form equations. Also very, very important. And all these regressions are estimated by using OLS. So it's very straightforward. There is no complication about this at all. Now coming to another example. So I again, give you an example. I've all used annual data, index of industrial production, value of exports in dollars, value of imports, foreign direct investment in dollars, annual rainfall, price index, time trend, exchange rate, and GDP per capita. Okay. So now coming to two-stage least squares. Now two-stage least squares or the generalized classical linear regression method. This model is widely used estimation procedure as it is applicable to exactly as well as to exactly. So please remember, if you have got a just identified or exactly identified equation, you can still use two stages. They say it's better. Okay, yeah, as well as over-identified equations. The least square method is applied in two-stage methods. So consider these. Suppose this is your equation. Apply a least square method to estimate the reduced form parameters in the reduced form model. Okay, so you'll use a reduced form. Then in the second stage, instead of using the original variable y, you use y hat. Instead of using, maybe I'll go back to this example. Sorry. Now here, you will not use IIP. You will use IIP hat. And where do you get that IIP hat from here? This regression will give you that IIP hat. So that is the change that you make between traditional simple equation regression. And so I will use IIP hat. I will use AP hat. I will use X hat. I will use M hat. I know then these hats are not correlated with the error. So that is the idea. That is the idea. Okay, so that's a two-stage, you'll understand. Now, which method is better? Three-stage least squares have not explained over here because it is done jointly. So the estimation is done jointly, or all the equations is done together. You may find it a little difficult to understand, but those of you who you cannot explore. So come back. OLS is an individual is used for a single equation. It is biased, it is inconsistent and inappropriate when you have this problem of simultaneity bias. However, they have smaller variances and less sensitive to data and specification. Okay. So that is it. Now coming to single equation estimators, the single equation estimators versus two-stage least squares and LIL. Okay. So compared to a single equation estimator, the two-stage and LIM is higher. It's more consistent. Now, two-stage least squares will be equal to limited information maximum likelihood estimator numerically if it is exactly identified. So if your equation is exactly identified, instead of using LIML, which is a little difficult, you can use two-stage least squares. For the over-identified equations, two-stage least squares and limited information maximum likelihood are asymptotically identical. So remember that. So when it is over-identified, either you can use this or you can use this, whichever you like. Advantage is two-stage least squares over LIML is very simple. Advantage of LIML over two-stage least squares is that it's a little more complicated. Then, supposing you use the three-stage least squares or the full information maximum likelihood. Advantage over the single equation estimated is greater, much more efficient. Three-stage least squares, no gain if equations are exactly identified or errors are uncorrelated across the equations. So if your equations are exactly identified, don't use three-stage, you can use a two-stage least squares. Full information maximum likelihood, no gain if equations are exactly identified. So you can use three-stage least squares and FIML over two-stage least squares because it gives you more efficiency. It gives you more efficiency and greater consistency. However, greater efficiency gain over both three-stage and two-stage if the error terms are uncorrelated and if the information is used in FIM, that is full information maximum. These are subtleties which you have to continue to work and try to understand. What are the disadvantages of these methods? Is they're computationally more complex, but that's not an issue because you're going to use a program to solve it. And it is sensitive to misspecification. So whenever you specify a model, it is assumed that the model is theoretically correct and now there is no misspecification. But if you do specify a model wrongly, it is quite likely that you could get into it. So that's about the estimation. So that is about it. Now I'll just show you. Now I'll just show you a demonstration in Python. Okay. So we're going to estimate it. I've already done the coding. Simultaneous equation models. So it's quite easy. So once you know the theory, most of the things you can get from ChatGPT, DeepSeek, Claude, Gemini, and all. So it's not very difficult anymore. But the theory has to be understood. Okay? So let me just show you how it is done. So simultaneous equation models, I'm doing a demo with some real data. So we always, as we normally do, you have to install this package called SEMOPY. SEMOPY. Otherwise, it won't do simultaneous equation models. Okay, you have to install this. Pip install SEMOPY. Okay. So since I've already installed it, I'm not showing you. Then I'll have to install all these regular packages that I use. That is pandas, numpy, matplotlib, OS. These are just very generic packages that I use in any Python session that I may start. Then I've kept the data. I'll just show you the data also. It's red. I'll just show you. I've created a file called macro4, right? I got a file called macro in different sheets. It's a little cumbersome. Here I've calculated what is the deficit of the government, which I've hypothesized, depending on your model. Then I've seen what is the credit flow to various agriculture, credit flow to agriculture. Then here I've taken the per capita GDP of India in real terms. I had to convert it to per capita. I have GDP and I also got the per capita GDP. Right. Then I've taken the exports versus imports. I've got this last one, current account. There is exports minus imports, so you can see it's negative. Then I've taken the wholesale price index, industrial production. I've taken the index of industrial production, index of agricultural production. All right, index of agriculture. Like that, I've calculated the exchange rate. And then I've taken balance of payment because not used. Then I've taken total employment. Then I've used money supply, total money supply in the economy. Then the total amount of rainfall I've captured. And I've also taken, just as a proxy, I've also taken oil prices, only meant to demonstrate to you. It's all in a folder called data. Okay. Then in this particular file, I want to know what are the sheets, because because each data is stored in a different sheet. So when you do it practically, also you should know how you do it. So therefore I've taken it, and this tells me what those sheets. So this command is sheet is equal to PD Excel file macro XLSX will tell me all the sheets in this Excel file, all the sheet names in this Excel file. Otherwise, I have to open the Excel file. So to avoid that, I do this command, and that's a sheet underscore names. It gives me the list. So I've got credit, I've got GDP and all that. Oil, the last one is oil, you would have seen. Now what I'm going to do is I'm going to read each of them into Python one at a time. They're all in this file, but they're in different sheets. They're in different sheets. I'm going to read it. As you can see, pd.read x underscore Excel, name of the file, sheet name is equal to first deficit. Then I did credit and then GDP. It's not theoretically very correct. It's just meant to demonstrate to you how it is done. Okay, there it is. I've read all the sheets. Now I want to combine all the sheets into one file called pool. Now I've got it in different sheets. Deficit is DF underscore credit. The last one is DF underscore oil. I want to combine it into one file called pool. For that, I use this command concat, pd.concat. And within square brackets, I give the names of the two files, deficit and GDP, access equal to 1, meaning it'll club the rows. And then I say join is equal to outer, meaning it'll take all the values, the larger from both. Then once I get this pool, then to pool I add export import. To pool, then this pool will have these two. Then to this pool I will add exports, and the last one I will add all the pool will have all these files. To that I'll add oil, and pool will be a very comprehensive file which you use. So this is how we pool data. So I've already done it. Now the name of the file is called pool. So I'll say pool.info. Just I want to see what are the variables that are there. It's got a long list, some are necessary, some are unnecessary. And this was, I don't need to look at it. Okay. Then I look at the shape of this file, what we need now. Then they say 73 rows, 93 columns. Then I'm specifically interested only in these columns. I'm interested in 43. 43 is course serial, right? Right? I'm saying I want all the rows. I want 43. And then I want these other ones, 0, 3, 10, you can see. 0, year I want. 3 is gross fiscal deficit. 10 I want gross domestic product. Like that. So I pick out the variables that I want, because in other words, I'm going to subset this file into a file called into a data frame called df, and say pool.ilog, right? And then I will take all these variables, right? And I will 92. You just see 92. 92 is crude oil price, world crude oil prices. So I subset it. Then I just wanted to look at the data from the bottom, and I see some little inconsistencies are there in my data. Right? Okay. Then what I do is, here what I noticed is, I found that there are 2 years with the same thing, and one has been shown as blank. So I thought I will just take a mean of the two values, because it's being repeated. This is only out of convenience. It's not something out of this thing. So what I do is I do a group by, and I say group by year. All the variables that I want, all the variables that I want, I just group by, take a mean, just in case it's anything duplicated. And then when I look at the list, I get the tiny list of variables that I want for my simultaneous equation. I got deficit, I got domestic product, I've got per capita GDP, current account data, all that. All my variables are there. Okay, then now when I look at the tail, I notice that it's 21, 22, 22, 23. So the problem is solved. I had a problem with the index of industrial production. You notice that you get like this, it got duplicated. And as a result, you get the feeling that it is two different things. So it's been sorted out. This is only a matter of technical detail that I do it with. Then I can have a look at the graph. So here, so in Python, you can say fig.axis, plt.subplots, 4 rows, 3 columns, figure size also I've specified. And then I plot them. I take 0 is always starts with 0, 0, 0, 0, 0. Okay, so that is, it will give me the plot and it will also give me the title. So plot and gives me the title. Plot gives me the title. So it's same 0, 1, 0. Okay, so that I do all the variables. So first I will have a look at all the variables. This variables. So I get the idea of what my variables look like. Then I say gross fiscal deficit is going up. The per capita GDP is steadily rising. Current account, the total is coming down. Index of industrial production going up. So Corona, it came down a little bit. Agriculture production going up, exchange rate. So I get a bird's eye view of what exactly is happening. World to world, what's happened to world crude prices, what's happened to exchange rate, all that. Money supply, foreign direct investment. Rainfall, of course, got deeply duplicated. Okay, so now I've got a visual appreciation of the data that I'm going to use. Then I'm going to specify. Now, this is the important part. Okay, here what I'm trying to do is, I am, kind of cleaning the data. I'm cleaning the data. I'm resetting the index. I'm converting it into a range. What you notice when you look at the data. Now, when you look at the data, you see the data is like this: 1890, 1890. So here you're using time series data. And when you use time series data, the problem is whether it cannot read 1890. This should be either 2018 or 2019. So I've gone to ChatGPT and got this code. And what ChatGPT said, you just do this. You just do this. You have to remove all the missing gaps and all that, all the commas, and check if there are any missing values. One of the biggest problems when you do any kind of analysis in Python is there should be no missing values in the data. So what I do is is.isNull, df is the name of the file, dot isNull, open and close the bracket, sum, open and close the bracket. Now it says that none of your variables has any missing values, null values. Okay, now this is important. From linear models dot datasets import ROZ. We have to import that file. Then I convert, now I'm going to change my file, which I call df. What I call df, I'm going to convert it into a new name called data. So I'm going to convert it into a new name called data. These are the variables that I'm going to use for my simultaneous equation model. This I need not look at it over and over again, so I'll just close it. Okay. Now what I want to do is I want to clean the names of the data. You'll notice, look at the names of the data. Look, there's a gap and there is a 3-2 and all that is very untidy. But even R and Python have a difficulty reading the data. So in both the programs, you have this program called Janitor. So first you must install it. I've installed it already, so I'm not going to install it again. So you say pip install py janitor. And once it is installed, then I can import janitor and I say data is equal to data.clean names. So the names which look like this, after I run this code, you see it gets cleaned out. All the gaps are removed, brackets are removed, percentages are removed. Everything is made lowercase. Persons has got one gap before and after. Persons have got one gap before and after. Something, it cleans the titles. It cleans the titles. So then I take this, I copy this, I make these my names. This is what I'm going to use in my simultaneous equation model. I copy it here and I paste it over here and I call it data. Okay, I'll give the name. So these are my new variables that I use in data. Okay, here, now that you're familiar with these terminologies, I'm now going to explain my exogenous variables. Okay, so I'm saying my exogenous variables are fiscal deficit, current account deficit total, foreign direct investment, and all that. So that you don't worry. Now here is where we are going to do the linear program. Sorry, the simultaneous equation models is going to start here. So from linear models, import instrumental word variables 2-stage least squares, instrumental variables 3-stage least squares, seemingly unrelated regressions, instrumental variables, system, GMM. So please understand that these are the estimators of the simultaneous equation model. Two-stage least squares, three-stage least squares. So SUR is the full information maximum likelihood estimate. And the fourth one is the GMM. It's called the generalized method of moments estimator. Okay, these are the estimators. So I'm going to import these estimators. So I run it. So now I'm ready. So you can solve your simultaneous equation very easily. So first I'm going to, my first model was a GDP model. You please recollect what we did over here. Please recollect what we did over GDP. So I first specify the GDP. And I'm going to use two-stage least squares because it's over-identified. Over-identified. I will use two-stage. I can use three-stage. But I'm going to demonstrate. You can just use it yourself and try to experiment. So I say IV, same thing. SLS in bracket. What is my dependent variable? My dependent variable I should choose from what I have. So my dependent variable is this. Per capita GDP. Dependent. It is from the file data. You don't forget when we got the data here. So as you declare, so the job becomes very easy when it comes to estimation. I declare my dependent variable per capita GDP. I declare my exogenous variables. Exogenous variables. Now, exogenous variables are those variables that you have in the model. Look, I've taken foreign direct investment, gross. So I'm saying GDP is dependent on foreign direct investment. Okay, these are also exogenous variables, but they are endogenous in nature. So I will say index of industrial production, index of agricultural production. So if you just go back here, it is this. Index of agricultural production, export, import, low trade. Now I've slightly modified it over here. So you can just see. So you have to declare your model. Here you have to give the instrumental variable. The instrumental variables are the variables that you do in the reduced form equation. These are called the instrumental variables. All these will be there. But something you should remember. If I'm going to use one of the instrumental variables as an exogenous variable, I should take it out from here. So if I, for instance, let me just show you. Okay, I'll run this. So these are my instrumental variables. These are my dependent variables. These are exogenous. These are endogenous. These are my independent variables. And please see, gdp.res is equal to gdp model.fit, covariance type unadjusted, print GDP. Here it is. So this is the model. So foreign direct investment has a positive effect on GDP, but it is not significant. Gross fiscal deficit has a positive effect, but it is kind of significant. So if the government has budget deficits, because in order to spend, if the government creates a deficit, it's good for the GDP, because that is why governments go in for budget deficits, not as if deficits are bad, because it was so bad then the government wouldn't have got for deficit. Then you take the index of agricultural production has a negative effect. Sorry, the interesting thing is index of industrial production has a negative effect. Meaning, if the industrial production increases, the GDP, per capita GDP will come down, meaning it does not help per capita GDP. So when you follow a system of over-industrialization, it does not help your per capita. You're not talking about total GDP, you're talking about per capita GDP. And what you notice, it is highly significant. The interesting thing is agricultural production is positive. Positive and significant. So agricultural production, increasing agriculture, investing in agriculture helps in increasing the per capita GDP. And that's exactly what Brahmanand and Vakil's wage good hypothesis of development really were trying to advocate. That you must invest in wage goods, less on capital goods, particularly when your country is in a lower stage of development. So this is the first. Similarly, you do for all the other equations. Now you take the second variable, that is, of course, this is repeated, sorry. This is repeated. Then you take the second index of agriculture, industrial production, GDP, IV two-stage least squares, index of industrial production. You give all your this thing, index of agriculture, rainfall comes here. So what you notice when I put rainfall as an exogenous variable, I should take it out from here. I should take it out as an instrument. Though rainfall is an instrumental variable, we know that rainfall is an instrumental variable. But I have to take it off when I'm treating it as an endogenous variable. Please remember that. Otherwise, you'll get kind of stuck. So here we go. We estimate that's in index of agricultural production. So we say foreign direct investment has no effect, obviously, because investment is not in agriculture. Industrial production has a significant effect, lagged industrial production. So this year's industrial production does not affect agriculture, but last year's, but that's what you may notice. I've lagged it. I said dot shift one means I lag it one period. So I tried this out, and that's why I thought current industrial production, because it's not prepared. Look, you see, current industrial production has a negative effect. So that's why I included lagged. I said if current has a negative effect, then lagged has a positive effect. So industrial production is good, but with a lag of 1 year. Per capita GDP also affects industrial agricultural production because as the GDP of the country goes, agricultural production also increases. Then I've done it for industrial production. So I've taken lagged industrial production as a variable. There you are. Foreign direct investment has a negative effect, very surprising. Lagged industrial production again has a positive effect. That is, last year's industrial production will affect this year's industrial production. Current account total, that is your trade has a positive effect. Yeah, trade has a negative effect. That is more the trade. We got that elsewhere also. Agricultural production has no effect on industrial production because it's not significant. Per capita GDP has no effect. So GDP will not have any effect. So depending on these results, you can keep revising your model. Then now I'm going to take trade. That is export minus import, current account deficit. So the exogenous variables are foreign direct investment, lagged foreign direct investment, US dollar, that is exchange rate. I've taken exchange rate. Plus, I'm whether the agricultural production, industrial production, and per capita GDP has any effect on the trade. So the instrumental variables are declared. I say fit, and I will get them. So you will get results for each model one at a time. So now this is the trade model. The trade model says foreign direct investment has no effect on trade. Lagged foreign direct investment has a very significant effect on trade. So this year's obvious. It's obvious. So this year's industrial production has no effect, but previous industrial production has lagged has an effect. So dollar exchange rate has a positive effect on trade. That is very interesting. So as the country's currency gets devalued, export minus imports get wider. And it's significant, and it's very significant. So like that, agricultural production has a very significant effect. Industrial production has a very significant effect. GDP also has a very significant effect on trade. So if India is trying to go good with all the problems we're having in America, so if you have to increase our GDP and increase our performance, we have to increase our trade. We have to become trade competitive, and you can trade. So this way, you can go on fitting your simultaneous equation models rather easily, but the specification of the model is very, very important. Now here, let me take a little digression. Someone will turn around and say, okay, now you say this is your GDP, per capita factors contributing per capita GDP, you analyze in the two-stage least squares framework. Let me use a simple regression. How do you say that simple regression is better? You say it is inconsistent, you say it's biased. So I'm going to now fit a simple regression. Dependent variable is per capita GDP. Independent variables are all those variables, FDI, gross deficit, index of industrial production, index of agricultural production. Maybe I can use foreign direct investment also. I'll take FDI. And let's see how it affects my. Yeah. Yes. So this is called an OLS regression. Please remember, when I fit an OLS regression, I use stats-models.formula.api and all that, and I will test it. So here I will get a regression. Yeah, here I've got a simple regression. Now look at the coefficients. Foreign direct investment has a positive effect, significant effect. Foreign direct investment has no significant effect in the simultaneous equation framework. But in a single equation framework, it gives you the impression that it's significant. Index of industrial production has no effect. Index of agricultural production has a significant effect. Index of agricultural production has a significant effect, and so on. So this is what we mean by consistency and wrong sign. So we use a single equation model instead of a simultaneous equation model. You will end up with results which are wrong. What the computer does is it converts these single equation, the endogenous variables into instrumental variables. So I'm going to regress per capita GDP on all of this. Right? I'm going to do a per capita GDP. I'll call it, this is called RLS, reduced form. These are my reduced form equations. These are all exogenous variables, which I said strictly exogenous. So what you got here is the reduced form equation. You get the reduced form equation. This is the reduced form equation for GDP. So I will not use this as a variable in that regression. I will not use this as a variable. Instead, I will use this. So if I want to know what is the effect of foreign direct investment, I want to see what is the effect of foreign direct investment on GDP. Okay, it is not. I can find out what is the effect of gross fiscal deficit. So the effect of gross deficit, the partial effect is this 0.003 is the direct effect. The effect of gross domestic is correct. The gross fiscal deficit on GDP is 0.002 crores. Whereas if I want to get that is the direct effect. The effect of gross fiscal deficit, the total effect is 0.0027. So the reduced form equations will give me the total effect of a variable on the endogenous variable. So the gross fiscal deficit, the total effect is 0.0027. The direct effect is 0.00. Yeah, take this. This is a direct effect. Total effect is this. So 0.0005 is the indirect effect. So gross fiscal deficit will affect something, and that something will affect the GDP. Okay, so this is basically what I wanted to explain and discuss with you about the simultaneous equation models. Rather easy to estimate when you do it in prep, but you have to specify the model correctly. But one thing that you should remember is when you build a system of simultaneous equation models, you should be very careful regarding how you construct the variables, how you choose the variables, and finally build the system to be as realistic as possible. I've told you the concepts, the nuances involved in simultaneous equation models, and not really got into how a correct simultaneous equation model system is to be formulated. That is a challenge that every researcher faces, because the models that he faces will be constrained by both the availability of data and an understanding of the reality. So to the extent possible, one has to understand how the system works and try to model it using the best possible variables for its use. Now, other than the conventional two-stage least squares, indirect least squares, estimators, you have other estimators which I mentioned, which I'll just briefly show you how it is done. So you have estimators like three-stage least squares, you have estimators like full information maximum likelihood estimators, which is nothing but the Schur estimates, and things like that. So they can all be done, they're available. So first what I do is I continue the same thing, the same data. So these set of codes that you can see, what I'm trying to do is I'm trying to replace all the missing values with one type of missing value, and then I drop them all together. And when I check these missing values, you find that there are no missing values, and we can go into the next step. So the choice of the estimator will be something that you have to decide based on your study and understanding of situation. I'm just showing you how this can be done in Python and how the coefficients are obtained, and you will notice that the coefficients are very different from one estimator to the other. So when you use simultaneous equation models, you should have a complete understanding of which estimator to use, because we notice that when these equations are over-identified, you have a range of estimators that you can use. So you must check the assumptions underlying the use of an estimator and only then use it. I'm only trying to demonstrate how they are used. So you have the first information maximum likelihood estimator. I've used the same set of data. So I'm just showing it to you for one of the equations in the system, and that is for the trade, the current account deficit total. The independent variables were the same as we had before, and I'm now going to use a full information maximum likelihood estimator. You can just see FIML. So I just use it. I just use the word FIML model XYZ. You can get this from ChatGPT and things like that. And then we get a model. And this is the model that you get. There's a constant. There's a foreign direct investment has a negative effect, very significant. The lag dependent variable is also significant. the exchange rate is having a negative effect. That means the higher the exchange rate, lower will be the current account deficit, which means that trade will improve and the gap between the exports and imports will reduce, and that is significant. Index of agricultural production surprisingly has a negative effect, and so also index of agricultural production, and the GDP has a positive effect on our trade. So this is what the full information likelihood estimator gives us. So let us just go and see what did the two-stage least square estimator give us. We use a two-stage least square estimator, and these are the coefficients. Just look at the parameters, and you'll notice that they're different. That's what I want to appreciate. I want you to appreciate over here. So you have to decide which estimator you're going to use. You can see that there is no constant here, but there is FTI is minus 555, and here the estimator is 8733 lagged FTI, that's all. So it's a little higher. The negative effect is a little higher. Now here the lagged is positive. Just look at that. Lagged is positive, and the lag is negative. So you need to develop. This is significant. There is also a significant. Okay. And there are other ways of doing it. So this is the full information likelihood estimator. Then you can use the common these things like this, right? And then you specify each equation and give it a name. We call it GDP, you call it industry, you call it agriculture, you call it trade, and you hold set. This is another way of doing it. There are various estimators, and here you have defined the instruments. We talked about the instruments as being the exogenous variables in the system. Okay, so I first run that one. One is being run. This is because I don't run. And 101 is run, and then it takes the instruments and then it runs these equations. It's just declared it. It's just declared it. I think here it's where it does it. Here now it's going to use a two-stage least squares, slightly different from what we did earlier, but you need to check and understand how it is done. Okay. So we just got. So the advantage when you do it together, like there when I showed it to you earlier, we were doing one equation at a time. Now carefully observe. Now I first define the equation as GDP, and then I declare what are the variables, and these are the instrumental variables. Then I take index of industrial production, and then I declare the independent variables, and so on and so forth. Okay. And then I declare this. I say, I'm creating a dictionary. I call it equations. I'm creating a dictionary with GDP, industry, agriculture, and trade, right? Then I use the two-stage least squares and fit. And in this method, you get them all together. You get all the simultaneous equations together. First simultaneous equation which is per capita GDP. The second simultaneous equation for index of industrial production. Third industrial equation for index of agricultural production. And the fourth one for trade. Okay, maybe I should have declared it. Should have called it. Yeah, trade. Okay, so should have been current account deficit. Okay. So it's like just see. So this should have been current account. This slight difference is this should have been the variable rather than the order. Okay. You can make these changes, run it, and you get the trade equation, and you say from the trade equation. So which is the appropriate one? It's for you to study. I'm just showing you how it is to be estimated using Python. So if you use these set of curves where you declare each of the variables, somebody called the structural variables, the structural equations, and in square brackets you give the independent variables, you will get all the equations one bit of the other. So this becomes a little easier. So the same thing, there are other ways of doing it. Here also, you can do it this way. There are many methods. You can get it from the net. You can get it from ChatGPT. You can get it from DeepSeek. You can get it wherever. So here he's declaring the exogenous variables. Foreign direct investment, broad money. And then he's declared the endogenous variables. Okay, he's declaring the endogenous. So these are much more convenient than what we showed earlier. And you run it. Right? And you get all the equations one at a time. Okay, these are easier to use because simultaneously you will solve all the equations one after the other. Then I was also telling you that you need the reduced form equations, because reduced form equations give you what is the total effect of each variable on the endogenous variable. Because reduced form equations, each variable is regressed, each independent variable is regressed on each endogenous variable one at a time. So a particular coefficient like how does US dollar affect GDP, that is exchange rate. How does it? You can say this is the total effect. The total effect. If you're in the GDP equation, the total effect of US dollar will be negative 21.03. So this is the total effect. The equation corresponding to gross domestic per capita GDP will give you the direct effect. So this code, this set of codes, you can just see. I say PD data frame were reduced form results, declare the variables, and parameters were for endogenous variables, and it will print the reduced form. This is what it does, and it prints a beta matrix. It is just a one-line code. One-line code. Okay, it's just taken the endogenous variables one at a time and done a regression using the variables in the regression, and we will get the direct effect. So what is employment's direct total effect on for a 1 unit increase in employment, whether lakhs or millions, the per capita GDP will increase by 10.70. That's the total effect. So if employment is in the GDP equation, in the structural equation of the simultaneous equation model, that will give you the direct effect. So direct effect plus indirect effect gives you the total effect. So you can find out whether the total effect is positive or negative using this, right? So these are various ways. The codes are all there. So, this is another code which I got from the net. I want to find out how do these independent variables have, what effect does it have on the dependent? I run these and I get like this. So a 1% increase in the GDP increases GDP by what? But a 1% increase in the index of industrial production increases per capita GDP by 97. You read it along the row. So a 1 unit increase in the agricultural production increases per capita GDP by 295.7. So the diagonal elements will be usually close to 1. The diagonal elements will be usually close to 1 because 1 unit increase, what is the effect it's going to have? That is the rest of the indirect effects. So industrial production increases by 1 unit increase in the index of industrial production increases index of agricultural production by only 0.73. Okay, here you see index of industrial production will decrease the exchange rate by 505. Decrease. Decrease means it will improve. If the exchange rate decreases, it's actually an improvement in the exchange rate. Whereas the index of agriculture industrial production actually increases the exchange rate. So it's actually agricultural production helps to improve trade. Industrial production does not improve. Okay, just before I quickly finish, let me quickly show another method of estimation, which is called the generalized method of moments method, which I mentioned in the lecture. And this generalized moment is also constructed in the same way. You first declare all the variables. These squares have showed you a full information maximum likelihood estimator, which all the equations are done estimated jointly. And now I'm going to show you a generalized method of moment estimator. Variables are declared in the same fashion. And you can just see how you find this. This is a generalized method of moment estimator for two-stage D-squares. You have an OLS estimator of two-stage D-squares. You have a GMM estimator of two-stage D-squares, which is considered to be superior, which is considered to be more scientific. So when I do a two-stage D-squares with the entire system, I get using a GMM estimator, not an OLS, I get a different set of coefficients. So it is for you to go and study which is making more sense and which you need to use, because that is, it will require a separate lecture for that. It will require a separate lecture. So here again, the same thing with a slightly different estimator. There's a weighted D-squares. It's not just GMM. So this gives us a different set. This I leave it to you because there's no time for you to cover all that. I'm just showing you how it is to be estimated. Now what I've done is, now here what I see is, now you can see this. Okay, when you do, you'll notice that the output is this. This is the output of the GMM model, which we are getting printed up. You can see the system, GMM, results. This is the output. Right. That is the output. Now, using this output, I can predict the values. How do I predict the values? I put this system here, predict. Data is equal to data frame is equal to true, and I predict it and I'll get that hit. So now I will get the predicted values of the regression. How do you know our regression is correct? We need to validate, you need to cross-validate. So these are the predicted values, right? Now what I'll do is I will plot the predicted values with the actual values of agriculture. I'm just showing it to you for agricultural production. Okay, index of which we use as index of agricultural production, but here I call it agri because I've defined the agricultural production as agri. And now I do a graph for you. You can just see this is how graphs are done. Matplotlib.pyplot, figure size, plt.plot, and I get define one variable, plt.plot, I define the other variable. I define the labels, estimated index of agricultural production, actual agricultural production, line style, 2 dashes, 1 dash, marker is equal to 2. These are things which are useful and you need to know. Then my x-axis label is here and y-axis label is output. No, it's actually index of okay, index. We'll call it actually index of agricultural output. Estimated by actual is agricultural output. And he says a legend. I want to put a legend. These are all cosmetic things. And I want a tight layout, and here we go. So now the orange line is the actual. The blue line is the estimated. So you can see your model is barely it's predicting your, it is able to estimate, capturing the change in the, capturing the change in the, in the index of agricultural production rather than, except that it is later, the predicted is going up further, actual is actually kind of flattening out. This class, where we try to examine how simultaneous equation models are to be formulated. Theory is purely theoretical, and more importantly, how it is to be estimated. Okay, thank you.